Great. So the other talk before lunch is by Gautam Mandal, who's going to tell us about hydrodynamics of.
Thank you. Let me thank my co-organizers, Tridib and Jacopo, for inviting me to give this talk, quite contrary to the normal convention that organizers don't speak. I also thank several members of the audience who wanted to hear this talk. So this is about path integral formulation of hydrodynamics of 1D Fermi gas and some little excursion into 2D. This subject has appeared many times. Excuse me. So in case I don't cover my stuff, so here are the papers. So the first three papers are from 1992 and 93, where we discussed the many fermion systems with a fixed number of fermions, free fermions, in terms of phase-space hydrodynamics. So the slogan for this talk is going to be that phase-space density, phase-space distribution is a very convenient description of the configuration of n-fermion systems. And many of the beautiful graphs that appeared in Marcos's talk today, about the marginal distributions in terms of momentum, as well as in terms of position, they come out quite nicely in various examples in terms of phase-space distribution. So I'm going to explain that. And the path integral derivation of the action principle for the phase in terms of the phase-space distribution of non-relativistic fermions, they appear in this paper of 93. This paper was mentioned in Damson's talk, who has developed on this technology to higher dimensions, in 2012, and some nice recent work. Okay, and then we looked at the problem of quantum quench in matrix models. This is something that came from gauge theories and so on, and we mapped that problem to a Fermi gas again, and we found that the model actually equilibrated post-quench to a generalized Gibbs ensemble. So just a bit of history. At this time, we had no idea that there exists something called generalized Gibbs ensemble. So first of all, we were surprised that it's a Fermi gas, and it equilibrated, like Marcos said, and then it did not equilibrate onto the Gibbs ensemble. So that was the other surprise. So we thought that we were certainly doing something wrong. So anyway, I asked my condensed matter colleagues, and they said that yes, indeed, there is some very interesting recent works by Marcos Rigol and others called the generalized Gibbs ensemble. And then we matched our equilibrium values onto the GGE, and there was a perfect match. So that was 2013. And more recently, we applied this technology of phase-space hydrodynamics to solve this problem of shocks. So the one-dimensional conventional hydrodynamics in terms of density, real space density and velocity, it has this well-known phenomenon of shock formations. And shocks in terms of phase space actually correspond to something smooth called folds. And you can continue across very easily, developing, continuing the time evolution of phase-space hydrodynamics beyond shock formation, and you can go to infinite times. And what we showed here again, that there is a thermalized the equilibration to GGE, and from many different kinds of quantum quenches, starting from confining potentials of various shapes, and you just switch off those potentials, and then there are various power laws depending on the shape of the potential. And very recently, we have been working on the lowest Landau levels problems of 2D and some generalizations of that, some bit of which was described by my students here, Ajay Mohan and Surashe, who are here. And this was discussed by, so I'll go to this quickly. Okay, so here's a plan. Probably I'll do only 1 and 2, I don't know. So phase space hydrodynamics, first I'll tell you what this is in terms of the operator formulation. So we'll find that the Schrödinger equation for the fermions that sort of leads to a quantum Liouville equation using concepts like Moyle products and Moyle brackets, which are H-bar deformations of ordinary products and Poisson brackets. Then I'll go to the path integral derivation of hydrodynamics in phase space. So it will involve exact transformation from fermion path integrals. So it's really a derivation using the complete set of W infinity coherent states, which are like some W infinity is an algebra of one particle Hilbert space, somewhat like SU infinity, but it's little subtle. I don't have time to go into this one, but for this talk, we should think of this as basically some SUK group going in the limit of k going to infinity. Okay, and we'll find that the action that we find coincides with what is called a co-adjoint orbit action. Okay, so that's the path integral, and here, so then I'll discuss all this is exact and valid for any n. Then we'll discuss the large n limit, in which the phase space distribution, the Wigner distribution actually has the property that it actually becomes a density, and it's either 1 or 0, so leading to a droplet picture. And from the droplet picture, I'll show how the approximate emergence of conventional hydrodynamics that comes. And by the way we derive conventional hydrodynamics, the things which are still there, which appeared in Jerome's talk, and in many other talks before. So it will be clear that what are the limitations. Okay, and then some application to thermalization, etc. Okay, let's go. So we're going to discuss hydrodynamics in fermion phase space. The system is non-relativistic free fermions, n number of them, each of them subjected to this single particle Hamiltonian in some external confining potential. And let us introduce the second quantized fermion field, which, this is the oscillator corresponding to the wave function chi n, which are the eigenfunctions of the single particle Hamiltonian. So this second quantized fermion satisfies this Schrödinger equation, and it because we are in an n particle sector, there is a constraint on the Hilbert space saying that the total number of things then. Okay, so our basic dynamical object is going to be the second quantized Wigner distribution, which is this is people who are familiar with this single particle Wigner distribution, you just think of this size as the single particle wave functions. Now here I have just promoted the single particle wave functions to fermion second quantized fermion fields, and this is what is called the second quantized Wigner phase space distribution. So the idea would be to represent my n particle Hilbert space of fermions in terms of coherent states of this W infinity. Okay, I'm going to explain that. And the fermion path integral can be rewritten in terms of a phase space density variable, this little uxp t, which is an expectation value of the second quantized Wigner phase space distribution in an n particle W infinity coherent state. Okay, so I can represent all in-particle Hilbert states of the Hilbert space, okay, by using the completeness of coherent states, okay, and the expectation value of that will be my phase space variable. So I can describe the states themselves in terms of expectation value of this second quantized operator. This is pretty much like what you have in case of the classical spin, which is going on a unit sphere, and you can discuss this. This is a beautiful subject of coherent states. You can have coherent states of Heisenberg group, you can coherent states of Lie groups, and so on. There's a beautiful book by Perelomov, on the theory of coherent states, which we used a lot. Anyway, so you can derive from there that the Schrödinger equation that I described in the previous slide that leads to this Moyer bracket relation. Okay, that the time derivative of so this is like a quantum level equation, and this u variable here, just like in this example, the spin is actually a unit vector in 3 dimensions. Similarly, there's a relation here which is like u star u, the star product of u with itself is u. Okay, so I'll show how it comes actually in the quantum theory from the fact that the projection operator square is the projection operator. That's the basic thing from here. And then this is what comes from the this particle number. So the total number of particles is n, that's this one. This actually represents physically Pauli exclusion principle, as I will explain later on. So the star product here is defined like this, which you can see that it's an h bar deformation of the ordinary product. If you put h bar equal to 0, it becomes the ordinary product. And this Moyer bracket is defined in terms of commutator of star product. And this also, in the h bar going to 0 limit, it becomes a Poisson bracket. Excuse me, there should be f and g just like this here. Okay, all right. So let's go. So these are the 3 results that we would like to prove, and there are 6 ingredients that you need for that. One is the definition of the single particle Wigner distribution. Actually, there should be a plus here and a minus here. That's the convention that I'm using now. So here are examples that for wave packet states like this, the Wigner phase space distribution is also a wave packet, but now in phase space. And similarly, if you take the Hermite functions, which are the eigenfunctions of the harmonic oscillator potential, so then the Wigner distribution is given by some Laguerre function, and they are a function of x squared plus p squared. So as a result, you can plot them as a function of x squared plus p squared square root, like that. And as you can see, that it's a very, very highly oscillating function which goes to negative values. This is a standard thing about Wigner phase space distribution, that people didn't believe that this is any kind of a distribution at all, because it has, the density, because it has negative values. Okay. In fact, now the negativity of the Wigner distribution is used a lot in the quantum information literature to as a measure of quantumness of the wave function. Okay. So, however, when you take the n particle Wigner phase space distribution, that is to say, take the second quantized Wigner phase space distribution and take an expectation value in an n particle state, you can show that this becomes a sum of the single particle Wigner phase space distributions over the occupied states. And you can show that in the large n limit, so this is a graph, in the large n limit, the negativity goes away. In fact, it all sort of crowds around the value 1. So this expectation value here, And in the limit of n going to infinity, it goes to this theta function. Okay. So, so this is a plot for the harmonic oscillator. More generally, you can show that it goes actually to a theta function of this kind, where the single particle Hamiltonian, the classical Hamiltonian, is bounded by a Fermi energy. Okay, so it's given by a droplet, okay, whose boundary is the Fermi surface. Okay, so this you can explicitly prove in this case. More generally, you can show that all the fluctuations are near the Fermi surface, where you can you can use WKB representation for the wave functions here, and you can sum over these things, and you can show this result. Okay, so this is actually something that you can prove. So here's one more 3D plot, contour plot of this is how the Wigner phase space distribution looks like at n equal to 30, and this is the picture at n equal to infinity. This is just a spherical droplet. Okay, so and the boundary is given by the Fermi surface. Okay, there's a third ingredient which is very important. That's the Weil correspondence in the single particle Hilbert space. So corresponding to any operator, there's a phase space function, and vice versa. It's given by excuse me. It's given by this thing that given a phase given an operator, you take a trace of that operator with respect to this. This is sometimes called the Heisenberg-Weil operator or displacement operator, etc. So it has this structure, right? And you take a trace of my single particle operator with this Heisenberg-Weil operator, and the function that you get is the phase space function. So there's a and there's a similar relation that you can write down where starting from a phase space function you can generate the operator. So that's called the Weil ordering prescription, which you can read off from this itself. And this generating function, this G hat, the Heisenberg-Weil operator, that has an algebra. Okay, so this is an important algebra. This is what is called the W infinity algebra. In fact, this is a quantum version of the algebra of canonical transformations in phase space. Okay, so this is rather easy to derive. And then you can show that the operator product that actually goes to a star product defined already, and the commutator product of operators becomes Moyle bracket of operators, and which is given as before. Now, interesting thing is that if you take a density matrix rho hat, then the Wigner distribution corresponding to that density matrix. So suppose you had a mixed state given by this density matrix, then it is just given by the corresponding phase space function is the Wigner distribution for that mixed state. And if this was a projector, like it's a pure state corresponding to the wave function psi, then of course this just becomes an expectation value, and this indeed is the definition so if you go back to the definition of the Wigner distribution, you will find that this indeed is a Wigner distribution. So what do you learn from here? That the Wigner distribution corresponding to a pure state, Wigner distribution is just the phase space function corresponding to a state, okay, whether it's a mixed state or a pure state. All right. So we also get the Weil correspondence also includes representations of traces and integrals. So trace of an operator is given by the integral of this, and the trace of a product is given by integral of products. So this in particular also means the following things, that the trace of a projector, which is of course equal to 1, that corresponds to the integral of the Wigner distribution. So the integral of the Wigner distribution, this is all for a single particle, is 1. And the fact that projector square equal to projector translates to this statement that U star psi, U psi star U psi is equal to U psi for a single particle thing. Okay, so now let's go back to the n particle Wigner distribution. So we have already remarked that the n particle Wigner distribution in the ground state, okay, for the ground state, is a sum over the occupied states. And now if you take a star product of this guy with itself, then the off diagonals simply drop out, because the off diagonal star products, they correspond to multiplying two orthogonal projection operators. Okay, so they drop out. So only diagonals remain. So therefore, this sum becomes again U0. So you have this result that the n particle Wigner distribution also satisfies this property that it goes to itself under a star product with itself. And okay, furthermore, if you take an integral of this, okay, so that's like an integral of each of these objects, which was equal to 1, remember. So therefore, the integral of the n particle Wigner distribution is given by 1, given by n. So I had shown this for the specific case of the harmonic oscillator, but this is this generally true. Okay, now comes the the aspect of introducing coherent states to describe the n particle Hilbert space of the fermions. So the first ingredient of that would be what I call the sandwich homomorphism. So if you take an integral of this kind, okay, this is basically the sum over these O1 operators over all the particles. So that's given by this object. So psi dagger x, O1 is an operator, one particle operator, psi x integral. And if you take the corresponding integral for the operator O2, then it becomes like as if you are taking a commutator of O1 and O2 inside, and then you sandwich that with psi dagger and psi. So schematically, I would write this like psi dagger O1 psi with psi dagger O2 psi is psi dagger O1 O2 psi. This is pretty similar to what we already know about construction of Heisenberg spins in terms of this fermions or qubits, and the commutator of Si and Sj is given by B dagger, and inside you have sigma j. By using therefore the commutation of Pauli matrices, you can derive that Si Sj is equal to satisfies the SU2 algebra. So this particular relation I call commutation of sandwiches is the same as commutation of meets. So here you commute the meets. So this gives a representation of the single particle operator algebra, specifically the W infinity algebra in the second quantized fermion theory. So if you have an operator algebra in the single particle theory, this generalizes that to the second quantized fermion theory. Now consider a unitary operator, equivalently a W infinity group element. That is to say, I take a W infinity algebra element here, which is a linear combination of some those GXP, this Heisenberg-Weil operators, and I exponentiate that. So then I get a W infinity group element. The second quantized representation of this, so this is for the one particle Hilbert space. The second quantized representation of this is that you take the sandwich psi dagger A psi and you exponentiate that. Okay, this is what you should apply now on the ground state, which is the field Fermi C. Okay, so this F naught is my notation for the ground state, and so you take that and Yeah, sorry. So this little a here is defined this way. So little a is the single particle operator. And of course, it can be written in terms of the linear combination of this complete basis of operators, Heisenberg-Weyl operators. Okay, so now it is straightforward to see that this operation that you do of single particle, so I have constructed now a rotation in the n particle Hilbert space by using a single particle rotation. So what happens as a result here, so there's let me just say what the result is. That if you have constructed your new n particle n fermion space state to be f like that, then the expectation value of the second quantized Wigner distribution operator becomes simply sum of single particle Wigner distributions in the new occupied states. And the new occupied states are all basically a W infinity rotation in the single particle Hilbert space, namely this. Okay, so um tilde xp is a Wigner distribution for the state u e to the power I little a acting on chi m, where chi m were the original states, okay, where a is this guy. Okay, so therefore, all the occupied states are simultaneously, rotated by a single particle W infinity rotation, and these are the coherent states which are complete in the space of the n particle states. Therefore, I can describe the n fermion Hilbert space in terms of these, and I will show this how this sort of shows up in the path integral formulation as well. All right. So now, therefore, because the new Wigner distribution in the new arbitrary n particle state is also a state like this, which is a sum over the Slater determinants. Therefore, it satisfies the same properties, okay, because it's a sum of projectors again. Projectors onto some rotated state, but nevertheless, it's a sum of projectors. So therefore, it's u star equal to u, and this the integral is equal to n. Now you can see easily that if this uxp, okay, has a smooth h bar going to 0 limit, then there is a nice h bar going to 0, this large n limit here, which is n going to infinity, h bar going to 0, n h bar equal to 1, where the star product will just become ordinary product, and you can take this h bar on this side, okay, so it becomes n h bar equal to 1, so it satisfies the unit area constraint, so it becomes like a droplet of area 1, okay. This is, we're going to explore this, much more, a few slides later. Okay, all right. So now so therefore transformation from one n particle state to another n particle state, we understand in terms of this W infinity transformation. So the Hamiltonian is just one of them. Hamiltonian evolution is just one of them because the Hamiltonian is a single one body operator, and it's constructed out of a single particle Hamiltonian. And now, so for infinitesimal transformations, this is how the second quantized operator transforms again by using the sandwich principle, that it's so u itself. So remember, u is given by psi dagger gxp psi. Okay, this is something that we have used before, and the W infinity transformation is psi dagger a psi. So therefore, it becomes a sandwich of that. And by using that fact, and you can use now the the commutator of A with GXP, where this A itself is a linear combination of the various, it's a linear combination of GXP. So A is AX prime P prime with GX prime P prime, and then there is a W infinity algebra that I can use to say that this is given in terms of some new element of the the W infinity algebra, and which is obtained by using the structure constants. And by using this fact, I can show that the expectation value evolves by Moell bracket. Okay, under any arbitrary W infinity transformation, and in particular, if that W infinity transformation is just a Hamiltonian evolution, then this thing says that you satisfy this this quantum Liouville equation. Okay, so here's one example of how Fermi fluid configurations can be represented by W infinity coherent states, which are simply deformed droplets in the h bar going to 0 limit. This is a particular example of W infinity transformation given by a deformation of the single particle Hamiltonian by this small deformation. And when you apply that, okay, you can explicitly prove this. This is done in the quantum mechanics in a 30 particle example, and this is n equal to infinity. That comes from the solution of this Moell bracket equation, and you can see that these two agree. Okay, so now using these things, I'm going to just say how the path integral can be derived. The basic idea is that I'm going to represent the n particle Hilbert space in terms of coherent states of a group. The group in this case is W infinity group, and there is a well-known way of setting up path integrals, okay, in terms of coherent states. Okay, that's what I'm going to use. Okay, so I'm going to first review a little bit on how to do this for finite Lie groups, finite dimensional Lie groups. So, let's say that I take n free fermions, meanless, each of which is described by a k-dimensional Hilbert space H1, which is k-dimensional, and let's say that this is a certain basis of H1, which is I runs from 1 to k, and let's associate creation operators that each I is given by bi dagger on the zero particle state. And it's easy to where I'm considering these things as fermionic operators, okay, so which satisfy these anti-commutation relation. And it's easy to show that the Tij, which is defined to be bi dagger bj, they are simply generators of SUK. Okay, so that's this is a well-known representation of SUK in terms of fermionic operators, single fermion oscillators. So in the continuum limit, this k I'm going to take to infinity, and you should think of this Tij as essentially bi dagger bj, which goes to psi dagger x psi y, okay, which is just an integral transform of the Wigner phase space distribution. Okay, so now we want to derive a path integral representation of the time evolution kernel, which is this from from one n particle Hilbert space to another state to another such state. Okay, so we are as I said, we are going to represent. Okay, so let me just say a bit of group theory. So for this k-dimensional Hilbert space with n equal to 1, okay, which is the one particle Hilbert space, I have already said that the Tijs, they satisfy the commutation relations of SUK. So this turns out to be just the fundamental representations. N equal to 1 corresponds to the fundamental representation of SUK. Okay, because there are just there are just k number of possible vectors, okay, which corresponds to placing the fermion, the occupied states being here, 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 or here, and there. Okay, so that's k. That's the k-dimensional representation, and this for n equal to 2, this is just the antisymmetric 2-tensor representation of SUK. So that's corresponding to this Young tableau, and for arbitrary capital N, it corresponds to the totally antisymmetric rank n tensor representation corresponding to this Young tableau. So that's the group theory. And what I'm going to consider now is the following coherent state. So where I take an arbitrary linear combination of the generators given by theta j I t I j for this corresponding to, so this is a state and corresponding to a group element which is e to the power I theta j I t I j, where t I j is a kinematic matrix which I think I have defined here. This one, okay? It just has 1 in the ij's I comma j space and 0 everywhere else. So that's my Tij. So this is the group element, and corresponding to the group element, I have constructed this state, okay, which is a coherent state, a group coherent state. So that's the and now the okay. So one property of this coherent state is that the state G is the same as state GH, because there are states which will leave this initial state invariant. So that's called the stability subgroup of such elements is some H. And so the state G represents actually elements of the coset G mod H. Okay. So there's a completeness relation which you can read off from this beautiful book of Perelomov, equation number such and such, and for an appropriate measure on the n-particle Hilbert space. This is what I'm going to use now in order to compute the path integral by inserting time slices, and the infinitesimal kernel is going to be this thing. And okay, so the Hamiltonian term is just going to be trace of h times phi, where, okay, so this is an important concept, which is phi 0 ij. Okay, this is expectation value of bi dagger bj in f naught. This is very similar to the Wigner phase space distribution. So you can easily show that this Hamiltonian term, the Hamiltonian term is, it just becomes trace of h phi. So you can think of this as h xp u xp integral. Okay, that's what it's going to be. And then this other term, just the overlap term, that becomes like G inverse G dot acting on phi naught. So okay, there's a lot of steps that I'm skipping somewhat. So the infinitesimal kernel becomes this stuff, and the finite time kernel just becomes like an integral of the same quantity that has appeared here. Okay, so that's an integral. Equation of motion is given by this, and surprisingly, or in fact not so surprisingly, if you know this story of how the SU2 spin is handled in this fashion, the equation of motion can be written entirely in terms of this phi. Okay, so remember what am I doing? I'm moving in the space of n-particle n-fermion states by a group element. Okay, the expectation value of bi dagger bj in the original thing goes to this phi. Okay, where phi is a matrix, single particle matrix. So I can make a correspondence between all n-particle states to the group element or to this phi. Okay, and this the equation of motion can be written just in terms of phi alone. Okay, and now so this is the action principle that I obtain, but you can show that this can be just like the equation of motion. Even the action can be written entirely in terms of the phi variable, except that it cannot be written just like a dt time integral. You have to introduce a family of paths in some. So this is your actual path that you are interested in, for which you want to find out the weight to assign for the Feynman path integral, but you have to write it as an integral, as an S integral of this cap. So this is called a cap. This is very similar to, this is like a solid angle, for this W infinity spin. This is also called the co-adjoint action. So I'll just need, 5 minutes. Thanks a lot. Okay, so this is very analogous to the SU2 spin case, where this quantity just is a solid angle. Okay, all right. So there's an abstract characterization of the space of this little phi's. Okay, you can show that the trace of phi naught is given by n for an n particle state, and phi naught square is equal to phi naught. It's almost like what we saw for the u variable. And after the time evolution, also these things are preserved. So therefore, from the states. Okay, so the states are uniquely characterized by points of G mod H, and they are uniquely characterized by rank n projection operators. Okay, here you are. So there is a one-to-one correspondence between the coset elements and rank n projection operators. Using that, in fact, I can translate so remember what I did. I took the time evolution kernel from in Fermion Hilbert space, that I wrote in terms of this path integral. I forgot to write here it is. This dg. So that just becomes the space of rank n projection operators is given by the integral over phi with these two constraints. So the action I have simply repeated from the previous slide, and this phi, in the continuum limit, phi ij will become phi xy, which is psi dagger x iy, but that's just an integral transform of the Wigner phase space distribution, and using that fact, you can translate this path integral to a path integral in terms of so here, up to here, it is exact. I have not taken the large n limit, and the action principle is also exact. This is called the co-adjoint orbit action, and but in addition, we have also written down the path integral measure. Okay, so from here, of course, it's easy to show that the equation of motion, the quantum Liouville equation, it comes out, and so I don't have time how to. I will say just a little bit maybe how the conventional hydrodynamics path integral comes from here, from that path integral, and this is how it looks like. And here's the Hamiltonian, which has appeared in many cases before. So okay, so in the large n limit, some droplet picture arises, and okay, all right. So okay, I'll just say how the conventional thing comes. So suppose I take a droplet, which we say it's a quadratic droplet, okay, meaning that any constant x cuts this fluid profile in just two places, p minus and p plus. In that case, what you can show is that the density rho is given by the integral of u with respect to p. So that's just p plus minus p minus. Similarly, the momentum density, which is rho times v, is given by p plus square minus p minus square, because there's the integral of p with respect to e. So using that, you can find out what rho and v are. Similarly, the energy density you can obtain by integrating h times u with this integral over p, and that's p plus cube minus p minus cube, of course, with the potential term as well. So that gives you the, and then you rewrite this p plus p minus objects in terms of rho and v, and you get that. Equation of motion can also be derived from the this Liouville equation, and it just gives you the continuity equation and the Euler equation. It just comes from this fellow and this parameterization. Okay, this parameterization. All right. So, but of course, you know, the quadratic droplets have limitations because folds can arise, and you can show that, you know, where. So this is just to say, you know, how you can solve using Mathematica. You know, this particular thing is just you just evolve each fluid particle here by its own equation of motion, and that of course is well known to give the Liouville equation. And the point of the phase-space hydrodynamics, why it is more you know, suitable for describing time evolution, is that when folds appear, and this corresponds to a shock actually in terms of the original phase-space distribution, but because the fold is smooth and it just corresponds to tracking each particle by its own Hamiltonian equation, you can just go ahead and you know, go beyond shock formation, and you can go to asymptotic times to you know, show thermalization to GGE. This is something that we first found in 2013, and you know, we sorry, not this aspect. This aspect was in this the 2019 paper, that we can go beyond shock and show the thermalization. And the thermalization actually corresponds. There's a beautiful mechanism of equilibration to GG. So a fold forms, and you know, it touches the corner, this edge of the box, but the box is periodic, so it starts from here. So filaments start appearing, and all these filaments, you know, as time t goes to infinity, make it like a dense thing here, where the phase-space distribution is neither 1 nor 0, but is somewhere in the middle. This is only in terms of some coarse-grained picture, namely that any moment of the real space density sees this stuff, and this actually is a GGE. You can show that. Okay, so I don't have time to this one. We explicitly proved that it goes to GGE, and the approach to the GGE depends on what kind of Cohen's protocol you have. So there are various power laws that we derived in this 2019 paper, and you know, the last thing is that we have been able to apply this technique to 2D, but in case of the lowest Landau level physics, where secretly it's a 1D system, and I'm done basically. Okay, so the same filamentation happens in 2D, and these are the conclusions. So some open questions: H-bar corrections and quantum fluctuations from both the operator formulation as well as path integral thing. Higher dimensions, you know, does the path integral derivation work? So you saw in Son's lectures in a talk that there is a similar action principle we can write down. You can speculate from the coadjoint orbit action that I showed, and how does one incorporate interactions. So you can try to incorporate interactions which can be handled by mean field theory, and we have some preliminary result for the Gros-Lebeau model where you get some non-local equation of motion. Thanks a lot.
For quick questions?
Yeah. So, so for example, you know, yeah, that's a good question. What we did was the approximate derivation of the path integral in terms of this p plus p minus variables, which is rho v, and you can show that the sorry. No, the path integral itself. You can do loop calculations. You can do quantum loop calculations in the rho v formulation. In fact, there is some other you know, you can parameterize this u in terms of in some other parameterization where you can do some quantum. You want to know what we are doing with the path integral. So quantum fluctuations. So you can do some quantum fluctuations, simple cases in terms of this rho and v variables, but you can also show that there are divergences which appear in this conventional variables, which you can cure by going back to the original u variable, where the cure is given by essentially replacing the divergences. Wherever divergences appear, you have to replace that by the Fermi level effectively. So that's what is actually embedded in the path integral formulation over U. So basically quantum fluctuations. You can handle quantum fluctuations. We have done some calculations. 1 over n corrections. That's right. 1 over n corrections. And there are situations in which you can take n going to infinity as well. And there is some other parameter in the theory. There's some critical. There's a criticality of the potential. So you can take a double scaling limit, and you can do infinity n as well in that one. That is of some interest in string theory, called the C equal to 1 matrix model, 2-dimensional string theory.
Great. There would be time for one more quick question, or we can get lunch. Rick?
Well, just a comment. So, I mean, I called it Matitsin-Abanov thing, but you wrote the same thing on the slide, and with references that were older. So I should change my name.
Thank you.
Okay, with that, I propose thanks to both the speakers, and we'll go to lunch.